We'll see set associative mapping. In set associative mapping, we will be dividing our cache blocks into sets. Okay. Example, in this one, I have divided into two sets. Okay. Now, what are we going to do is, we will be fixing, example, any main memory block. Let us take B5. So this block number 5, where it goes is decided by the set number. That means, either it will go to set 0 or set 1. That is fixed, like direct mapping. Okay. In direct mapping, each main memory block will go to fixed cache block, right? But here in set associative mapping, each main memory block will go to a fixed set. Okay, maybe it is set 0 or set 1. How I decide is, so I simply divide, because I have two sets, right? Then I take the block number of main memory, block number. So I divide that block number by 2, because number of sets are 2. Example, let's say B0, block number 0, right? So 0 will go to set 0. That means in set 0, the candidates for set 0 I will tell you. 0, block 0, then 1. When you divide 1 by 2, then what is the remainder? Remainder 1, right? That's why it will go to set 1. In that way, some logic, that's it, correct? Because we have two sets, then if you divide any main memory block by 2, then the remainders will be 0 or 1. Then properly we can map them to set 0, set 1. That's it. So all the remainder zeros will come here, remainder 1 will come here. So that 0 and 2, then 4, then main memory block 8. I am assuming that we have 16 blocks, then 8, main memory block 10, 12, 14 will come here, and in set 1, main memory block 1, 3, 5, 7, 9, 13, 15 will come here. Understand? Okay. Now, so 0th main memory block always will come to set 0. But in set 0 you have 4 blocks, right? Where it will go? That is again flexible, like associative mapping. Now, for particular set, in this particular set, we follow the associative mapping. That means, so 0 may sit here or sit here, anywhere you can keep if the space is free. Okay. If this space is not free, then we'll keep here. If this block is not free, then we'll keep here in that way. Understand? Then that mapping is called set associative mapping. Now, how we play with binary patterns, we'll see. So, in this binary pattern, if you see, the last digit, if you see, that will be for word number, correct? Because we have 2 words in every block, then this bit is dedicated for what? Word offset. Now we have 4 digits, right? 4 digits. So these 4 digits, if you see, for these two, first block, these 4 digits are showing 0, 0, 0, 0, 0, 0, 0, 0. That's why it is block number 0. In that way, easily we can, in our imagination, block number 1, but binary pattern for that memory address is 0001. In that way, we can map these two things. For us, it is block number 1, this one. What is the binary pattern for that? Last 4 bits are 0001, 0001. So finally, my binary pattern, or which is memory address. So what should be the size of memory address to have this kind of structure? How many memory blocks you have? 16, right? 0 to 15, 16. Each block contains how many words? 2, 32 words. Assume that, let's say, your main memory is word addressable. If it is word addressable, then how many addresses are required? 32. To represent 32 addresses, how many bits are required? 5 bits. In that way, so 5 bits will be decided. Now 1 bit is gone for word offset, then remaining 4 bits. So these remaining 4 bits will tell that the number of main memory. That means main memory block number. Always you remember, it's not only for set associative mapping. Generally, so these bits other than word offset will be representing main memory block number. Now what do you want? You want to know which set number it goes, right? How you decided? You divided block number by 2, right? What is that, the significance of 2? Because we have 2 sets. What if we have 4 sets? Then we would have divided that by 4. Dividing a main memory block number by 4 and getting some remainder is equivalent to here taking these bits from right to left. Both are same. Okay. Example, you see, this is 0000, main memory block number 0, right? If you see this first bit, that indicates the remainder if you divide that number by 2, right? If you divide block number 0 by 2, what is the remainder? 0. Definitely this one. Let us cross check with another one. See this one. This is a block number 0001. For block number 0001, main memory block number, this bit indicates that it is 1. Then if you divide this block number, which is nothing but block number 1, by 2, then what is the remainder? 1. This will be indicated by that. Okay. Now let us try to understand with 4 sets. Example, if you have 4 sets, okay, they are set 0, set 1, set 2, set 3. If you want to know which main memory block number will go to which set, then simple technique is what? Divide the memory block number by 4. Example, let's say you have a main memory block number 7, okay, then it should go where? If you want to know, take the main memory block number, divide by number of sets. Number of sets are 4. Then what is the remainder? 3. Then this main memory address 7, main memory block number 7 should go to set number 3. Then how to do the same thing, how to assert the same thing with memory binary patterns, I will tell you. Write 7 in binary pattern 0, 1, because see, I am assuming this number of bits, 5 bits, right? 0, 1, 1, 1. This is for, leave this one because this is word offset. Okay. Now we have remaining 4 bits. 7 main memory block number means 0, 111, right? This is main memory block number 7. Now focus on these two. Is it not remainder? You see directly 3. That's why these 2 digits are going to represent set of set, right? Which set it should go will be decided by the next bits. From now onwards, remember one thing, in set associative mapping, we divide our main memory address into 3 parts. The first part is word offset, understand? Now second part is set offset, that will decide which set this block should go. Now these remaining bits are tag bits, okay? These tag bits we know the usage of tag bits, right? Already we have seen, okay? Now example, how to map a particular main memory address I will show you. Example, you have one main memory address, let us take B12, okay? Let me take B12. In B12, entire this block number 12. What is the binary pattern for that block number 12? Block number 12 means 5 bits, right? 1, 2, 3, 4, 5. We know that these 4 bits represents block number. So write binary pattern for 12. This is 2 power 0, 2 power 1, 2 square, 2 cube, 2 power 4. 2 power 4 should be 0, 2 cube will be 8, 2 power 2 will be 4, right? 8 plus 4, 12. See, now this is for word offset, ignore it. So I am just talking about main memory block number. This is your main memory block number 0110. Where it should go? Because there are 2 sets, simply take this bit, right? 0. So that's why keep it in set number 0. In set number 0, where you keep this data, this block data? Anywhere, because there are 4 blocks, right? Anywhere you can keep, right? Wherever you keep. Example, if you keep in this second block, try to understand. If you keep in this second block, then there will be tag, okay? I am showing the tag here. This is second block. So example, you are keeping the data of B12, right? This entire block B12. Let us say this data is D. Keep the data D, okay, here. What is the tag for that data? I will show you. What is the tag? What is the tag? These 3 bits, 011. You keep 011 here. So searching will be easy. Now how to retrieve the data I will show you from the cache. First, your main memory address will be taken again, and word offset will be ignored first of all, because we are just searching for the block. Then this 0110 will be looked. Then this 0 will index to the right set. This is set index, okay? So using 0 you will index into the right set, okay? Then this 0 will index you to this set. Then you will come to this group of 4 blocks. But among them, which one is right? Then what we do is we compare every tag with our tag. What is our tag? 011, right? Mr. Tag, are you 011? No. Mr. Tag, are you 011? No. Mr. Tag, are you 011? Yes. Then definitely this is our data. In that way, so search will be done. In that way, we will look into the cache. Understand? So this will be definitely, in between direct mapping technique and associative mapping. We are not searching all the blocks, right? We are not, searching all the blocks, and we are searching 4 blocks. It's not direct mapping. In direct mapping, we'll search only 1 block. So it is in between direct mapping and associative. Now set associative requires how many comparators? Because we have to do comparison parallelly, otherwise it takes lot of time, correct? So that's why definitely we have to plan our hardware such a way that the searching process should done parallelly. That means we know that once what we do, I will tell you. First of all, we index into this right set. Once we go to right set, then we will connect this tag, this tag, this tag, this tag to 4 comparators. That means we use 4 comparators, one here, one here, one here, one here. So the other input of this comparators is our tag bits. Okay. So parallelly all the comparators will be compared, and one of them will give the hit, right? Whenever one of the bit gives hit, then we can directly take the data from that appropriate bit. Understand? So this is the way things will work. Now we have one question here. Sir, yeah, somehow your one of the tag will hit, right? Comparator will give the output 1. But how do you know that a particular comparator gives 1? For that, generally what we will do is we will use multiplexer. Okay, so this multiplexer will decide that. Okay, what we do is the result whatever you get, right, the tag results. Okay, so example, let's say this tag result is 0, this tag result is 0, then this tag result is, let's say, 1, right? This another tag result is 0. Then what we do is we connect these results 0 0 1 0 to this multiplexer. Let's say if I do that, okay, then this multiplexer is going to select one of the blocks among these 4 blocks based on these 4 results. We can plan it, not a problem. Understand? So what we do is this multiplexer will be connected to the results of the comparators. Okay, so if the result is 0 0 1 0, then we can say that, then we can select the right block. That which block? Third block. If the result is 0 0 0 1, then we will somehow select fourth block. If the result is 1 0 0 0, then we'll select the first block in the appropriate set. In that way we can plan. Okay, don't worry about that hardware part. Understand? So this is about set associative mapping. Understand? Now the number of comparators, if you want to know, exactly equivalent to number of blocks in the set, right? Now number of comparators in associative mapping is total number of cache blocks, right? Everything we have to search. Number of comparators required in your direct mapping is only 1, right? So that is the difference between number of comparators in direct and associative and set associative. One more thing. So one more question they ask in the GATE exam. They ask number of bits required in tag comparator. So we are going to have a comparator, right? That comparator is going to compare 2 inputs, right? What is the size of the input they compare? That is called size of the comparator. What is the size of the comparator? It depends. Example here, that comparator is comparing how many bits? Tag bits. That's why that will be decided by number of tag bits. Simply compute the number of tag bits. That number of tag bits are going to decide the size of the comparator. So simple. Understand?